chapter 2 and actually turn to section 5. What? Confusing. Believe it or not, our year is not quite long enough for us to cover every single section in the book. I guess we could double up, like we did in
Algebra 1. Oh, yes.
So every once in a while, there'll be sections that we don't cover. And our next test is going to be the last part of chapter 2. And I believe I'll have to get my paper out to look. The first part of chapter 3. Let me double check here what we are going to cover. Yeah, the next test will be chapter 2, sections 5, 6, 7, and 8, and chapter 3, sections 1, 2, and 5. So it will be a combination of part of chapter 2 and part of chapter 3. So we are going to jump to section 5 of chapter 2. That's what we are going to be covering today. And we are going to begin to learn some postulates. So we'll have to figure out what a postulate is. And it says here, or axiom. That's another word that is sometimes used in geometry. When we talk about geometry, our very first day, you may remember that we talked about things called undefined terms. In other words, we explained what they were, but we didn't have some official geometry definition for them. A point, a line, and a plane. Those were kind of the starting things, the starting shapes that we needed in order to build the idea of geometry, and we learned how to identify a point and a line and a plane, all that sort of stuff. Well, we need some other beginning things that we accept are true. When we talk about it, it should be obvious that, yes, that makes sense, those things are true, but we don't do what's called a proof of them. We don't prove that they are true. And that's what we're going to begin to work towards, is this deductive reasoning thing called a proof. Yesterday in career assembly, when the attorney mentioned, did you hear him talk about geometry proofs? I caught that when he said that. I don't know if you caught that. But he talked about an attorney needing to be able to understand logical reasoning and thinking in order to build cases or arguments, and mentioned that geometry proofs kind of use those ideas of logical thinking. That's not what he said.
No, I mean, that's what he said. I thought it was a geometry.
No, he said the geometry proofs were similar in the type of skills you had to have in order to do those things. So postulates. Postulates are true statements that we don't prove. We accept them as fact, and they're very believable. We accept them as fact, and then we use them as basis for arguments to build or reach other conclusions. So we're going to look at some postulates that deal with points, lines, and planes, our basic shapes that we have in geometry. So when they give us, and let me point out where it says 2.1 right here, when they give us a number for a postulate, there's nothing magical or significant about that number other than the fact that it is found in chapter 2, and this is the first postulate that they talk about in chapter 2. That's what those things mean. So at some point, you need to reference postulates. Well, you don't reference them by the number. You reference them by, sometimes they'll have a name, or sometimes you have to write them all out when you are using a postulate to help prove something or build an argument for something. So our very first postulate, it says, through any 2 points, there is exactly one line. So imagine that in your mind for a moment. If you can visualize any 2 points anywhere in space, do you believe that there is only one line that would go through those 2 points? Hopefully you can see that that's true. There's only one possible line that would go through those 2 points right here. And if I moved it, there's only one line, whatever this line is, that goes between those 2 points. There's only one line. So it should make sense. It's a true statement. It should make sense to us. They say, here's an example. Line N is the only line that happens to go through points P and R. There's not another line that I could draw. Remember, is this a line in geometry?
No.
No, that's not a line in geometry. The line straight goes forever. There's only one line that can go through those 2 points. There's not another line that you could draw on any location. So there's our first postulate. Let's look at our second postulate. Through any 3 non-collinear points. What does non-collinear mean again? Not on the same line. Through any 3 non-collinear points, there is exactly one plane. If you pick any 3 points that are non-collinear, there is only one plane, and exactly one plane, that would go through those 3 points. So let's see if I can't pick an example. Take the top right corner right over there. That's going to be 1 point. Right up here is going to be another point in that top left corner. And then my third point is going to be this corner of the desk sitting there. What plane goes through those points? The plane would be one that's kind of like a ramp. That is angled like this. And that's the only one that would go through those 2 points up there and this point down here. There's not another plane that can be drawn or visualized or that exists that goes through those 3 non-collinear points. That's it. There's just one. Now, they use this word non-collinear. Let's make sure we understand why they have to be non-collinear. Let's take those 2 corners again, and then I'll pick one right in the middle that's in the corner right up there. Is there only one plane that will go through those 3 points? Well, there are 2 that are built in this room, the ceiling and the front wall, but there's a lot of them. There are infinitely many. Think of this one that I drew right here in the air, that we imagined in the air that went through this point here. That's one of them. Or I could have another one at this angle, or another one at this angle, or another one at... You get the idea. There's infinitely many that would go through collinear points. So they have to be non-collinear, and then there's exactly one plane. And here they give an example. Plane K is the only plane that would go through points A, B, and C. They're non-collinear. Next one, a line is going to contain at least 2 points. Can it have more? Yeah, in fact, lines go forever, so they will. But I start with 2 points, and then I have defined a line, and then it can keep on containing more than just those 2 points.
So the only difference between 2.1 and 2.3 is 2.3 can have more than just 2.
So they're saying, yeah, they're very similar, but they're saying slightly different things. This one says there's only one line that exists that goes through 2 points. This one says if I have a line, it will contain at least 2 points. 2, 3, 4, 5 more. Next one, a plane contains at least 3 non-collinear points. So this one, again, is kind of related to the 2.2. This one, 2.2, said only one plane exists when there are 3 non-collinear. This one says, when I have a plane, it's going to have at least 3 non-collinear points. Now, it's going to have more than that. But we'll start out, there's got to be at least 3, and then there can be more than that. If 2 points lie in a plane, so here they've given the example of A and B, then the entire line that contains those points, and remember, if I have 2 points, then I know I have a line, and if the 2 points are in the plane, then it says the line is also in that plane. If the points are in the plane, the line has to be in the plane. So those are our first 5 postulates. Let's look at the next 2 postulates. If 2 lines intersect, then their intersection is exactly 1 point. Well, that makes sense, I hope. If I have 2 lines and they cross, they intersect somewhere, well, the point that they intersect, which means the point they touch, is 1 point. That's the shape, the geometry shape that they intersect or touch in. They're going to be 1 point. And if 2 planes intersect, what shape do they intersect in? What does it say here? A line. You take the ceiling and the front wall, that corner there where they intersect, that's a line. 2 planes will always intersect in a line. No matter how those 2 planes are oriented. I can have one like this and one like this, and they come together. Sure enough, that corner where they come together, that's a line. 2 planes will intersect in a line. So let's practice this newfound skill of ours about figuring out postulates that answer why something is true. Explain how the picture illustrates that each statement is true. state the postulate that can be used to show that that statement is true. So there's a picture over there. Hopefully you can see it. Line M. So here's line M going vertically over here on the left side of our picture. Contains points F and G. Point E can also be on that line. Well, you can see in the picture that, yeah, they drew points E, F, and G all on the line M. Which postulate matches what they have just said there?
A line that contains these 2 points.
A line, well, don't use the word that. It says a line contains at least 2 points. That's the one. So if we look over here, they talk about the edge of the building is the straight line M, and it has those points lying along those edges. So it's 2.3 which states that a line contains at least 2 points.
So whenever we get a question like that, can we put just that a line contains at least 2 points, or we have to explain the entire thing?
Well, depending on what they ask, but to answer the question which postulate, you say a line contains at least 2 points. They also ask, explain, show how the picture illustrates it. So that's why they said the other things. Line S and T. So let's look over here at our illustration. It's real light. Line S is this one here. Line T is this one right over here. Line S and T intersect at point D. Is that happening in our picture? It's happening in our picture. Which postulate verifies that statement?
If 2 lines are sitting there,
I'm hearing it. If 2 lines intersect, then their intersection is a point. Somewhere down here we'll be able to find that. If 2 lines intersect, then their intersection is exactly 1 point. Sure enough, we know that that is true. If we can find a postulate that agrees, it must be true, because we are making the assumption that our postulates are all true. It's kind of the foundation of geometry. So let's try this one. No picture to go with it. They just make a statement. And is this true? Can we find a postulate that says, yes, this is true? Points A, B, and C determine a plane. Determine, another way of saying make a plane. True or false? If it's true, tell me the postulate.
False.
True.
Well, we're certainly getting both sides of the argument.
They're not, it doesn't say if they're collinear.
Ah, there's the problem. They did not say those 3 points were non-collinear. Remember, to make a plane, to determine, when they say determine, it means it makes exactly 1. Determine, there's only 1. In order to just be a plane, those 3 points have to be non-collinear, because we have these 3 points in the corner. It didn't just determine 1 plane. There were lots of planes that could go through those. That's a false statement. Planes P and Q. So plane P, plane Q intersect in line M. I'm hearing true. Can you tell me a postulate that would back up your statement of true? There you go. This is going to have to be true. Now, of course, there can be different letters, but it's true because if 2 planes intersect, they're going to have to do some writing in geometry. Intersection is a line. So yeah, that must be true, because that's what's going to happen. Any 2 planes intersect, their intersection is a line. Determine whether each statement is always, sometimes, or never true. Then explain how you came up with this. If 2 coplanar lines intersect, then the point of intersection lies in the same plane as the 2 lines. Read through that again if you need to. Now there are 3 choices on this one. Is it always true? Is it sometimes true? Is it never true? Always. let me take, several of you said always. Is there a postulate that you think you could use to help back up your reasoning on always? I don't know what 2.6 is, but what is it? Okay, so if I first start and say, we have a postulate that says, when two lines intersect, their intersection is a point. So here we have a point of intersection. That point is on both those lines. So is there another postulate that I might put with it, that between both of them, you could back up what several of you said was always true?
You could say if 2 points lie in plane, the entire line containing those points lie in plane.
That is true.
There we go. Those are the two postulates. We've got one that says if I have two lines that intersect, they'll be at a point. And there's another one that says if we've got points in a plane, then the lines that contain the points are also in the plane. So everything's in that same plane. So I think the always statement was probably a pretty good conclusion to that one right over here. So this one must always be true. They said if 2 points lie in a plane, then the entire line containing those points lie in the plane. Both points lie in the plane, so any point along those lines must also lie in the plane. I liked how we said it too. B, 4 points are non-collinear. Sometimes? Anybody else? Sometimes? You can agree with it sometimes? So you're telling me it's not always. 4 points don't have to be non-collinear. Is that right?
Yeah.
Yeah, we can make 4 points that are all in one line. So it's certainly not always true. Never true. 4 points are never non-collinear. No, we can have them. Sounds like it's possible. And this one really doesn't have a specific postulate that goes with it, I guess. They talk about 2, 3. Sometimes, so we came to the right conclusion. Lines contain at least 2 points. Line can contain 2 or more points. Oh, there we go. So there's our reasoning that, yeah, we can have 4 because a line has at least 2. So it could be collinear. And you also could not be. There we go. They drew a picture even to help explain theirs. Let's try 2A down here. 2 intersecting lines determine a plane. Now remember, this determine says you will get exactly one plane if this is true. 2 intersecting lines determine a plane. What do you think?
Sometimes. Because you can intersect lines like this, the plane can't go like this.
Just keep thinking a little bit.
Always, because you have the other side of the line.
When do we determine a plane? Can you remember any postulate that talks about determining a plane?
We have 3
With 3 non-collinear points. If you have 2 intersecting lines, will you have 3 non-collinear points?
Yeah.
Yes.
Yeah.
You'll have to. They couldn't be all 3 collinear points, or there would be how many lines? There'd be 1 line if they were all collinear. So if I have 2 intersecting lines, and every line has to have at least 2 points, right? So they share one at the point of intersection. And then they each have an extra one over here. This is always true. You have to. I'll get a couple of meter sticks, and let's see if we can visualize it a little more. If I take any 2 lines, so Isaac, you stick this in some position. That's going to be our first line. All right, just like that. Now, I'm going to bring the second one. Let's say it hits right here. Now we'll make them flat just a moment. Is there one plane? Yes. Can you see that one plane right here? Is there any other plane that could exist that contains those 2? Not that I know of. I sure can't figure out any other plane that contains those 2 lines. We have to include these 2 lines in my plane right there. Look right at me. See the plane? Right here. There's the plane.
Visualize.
You see it? I mean, there's the plane coming right between you and I when we look at each other. Look at it. Always. three lines intersect in 2 points.
I don't get that question.
Is this always true? Sometimes true? Never true?
Lines intersect.
3 lines intersect in 2 points.
I can't visualize that.
Never?
Yeah.
Sometimes?
Oh, 3 lines. 2 points, right?
Yes.
Is it possible?
Yeah, sometimes.
Think of an 8.
Think of it. 1, 2, 3, 1, 2.
Sometimes.
Hunter said, think about the first letter of my name. Are those 3 lines? Do those 3 lines intersect in 2 points?
Yes. 4 points.
No?
So
So it could be sometimes.
Right. So we have to think carefully here. Did they say that all 3 of these lines are intersecting with each other? All they said was we have 3 lines and they intersect in 2 points. I've got 3 lines and they're intersecting in 2 points. Now, do they have to?
No.
No. So it's possible. So it's sometimes. Sometimes that's true.
Make like
One point.
Parallel line.
If you had 3 parallel lines, that would be a no, they're not intersecting. So you can make them where they don't. So there's more than one possibility happening there. Proof. What is a proof? A proof is a set of deductive arguments. There's something called deductive reasoning. Deductive reasoning takes a fact, and from that fact, there must be a conclusion that is true from that fact. And then that conclusion becomes the next step, where there must be something true from that. Takes us to our next step. And then we just keep doing that. One step at a time. We begin with something true. We take one statement that is true, and we have a reason for why it's true. And then we take one more statement that is true. We have a reason why that's true. And we keep on going until we've arrived at the conclusion that we want to prove. That's deductive reasoning. And if we can do that, then we have proved, or we have made a proof, that based on our original statement, there is some conclusion, maybe several steps later, that has to be true. And if something has to be true, then we say that statement is a theorem. It's something that is true, and it has to be true, but we can prove it by a series of steps, deductive reasons. And our reasons that we use in making these series of steps can be postulates. Or postulates are, we just went over about 7 of them. Postulates are statements that in geometry we accept them to be true. They're our building blocks. A postulate can be a reason. A definition, we're given definitions sometimes, like perpendicular lines. What are perpendicular lines? Yeah, 2 lines that intersect at 90 degrees. Those are perpendicular lines. They intersect at right angles. Those are perpendicular lines. They can be definitions that we know, oh, I know what this means. It means this. So what do we do when we do a proof? Well, first, we list the given information, and if possible, we draw a diagram. So often, geometry proofs are dealing with shapes or figures. So we draw the diagram that goes with it. And then we state what we are trying to prove. Sometimes it already is a theorem, and we know it is a theorem. We just have to figure out how it's proved. Or it's just some conjecture. In other words, somebody came up with some idea, and can we prove it? So first we state the given information, then we state what we're trying to prove. Then we create our deductive arguments by forming a logical chain of statements linking the given, what we started with, to what we're trying to prove, our final conclusion. And when we make those logical statements, we have to have a justification for each statement. So each statement has to have a justification. It has to have a reason to it. And reasons can be definitions. Maybe they're algebraic properties. Maybe they're postulates. We just talked about some postulates. or once we have learned some theorems or proved some theorems, then we could even use those theorems that we now know are true as reasons for other statements. And the very last thing should be the statement that we were trying to prove. Our last thing is the conclusion, oh, this is what we're trying to prove, and it has to be true. So let's look at a proof. Now, there are several different ways to do a proof, and the first one they show you is called a paragraph proof. This is like English class. You write a paragraph. It says, given that M, now this is point M, we know from our symbols in the geometry, when they just give us a capital letter, it means a point. Given that M is the midpoint of segment XY, write a paragraph proof that shows that segment XM must be congruent to segment MY. Now, it really helps if I have a picture or a diagram. Let me see if they did it. All right, they did it. To go with that. So step number 1 is going to be write what is given. Step number 2 is going to be write what is to be proved. And we also are in step 1 and 2 going to draw a diagram that goes on. So let's see where we start. Given. What was given to us? What was given is that we have point M, and it's the midpoint of segment XY. That's where we're starting. So let's make a picture. Oh, sorry. Here's what we're trying to prove. There's what we're trying to prove. That segment XM must be congruent to segment MY. Now let's draw a picture that goes with it. So this is what we're looking at here. So is there a way, if I have point M, it's supposed to be the midpoint of segment XY, I want to prove that segment X to M is congruent from the segment M to Y. Well, that looks like something that we should be able to prove. So let's see if we can make some statements. The very first sentence they say, if M is the midpoint, then from the definition of midpoint of segments, we know that the length from X to M equals the length from M to Y. What is a midpoint? If I ask you to define a midpoint for me. It's the point in the middle of a segment. Well, what does it mean to be in the middle? It means the two sides are equal length, is what it means to be in the middle. So they are combining their statement with the reason. So they say, by definition, we know that the length from X to M must equal the length from M to Y. So here they have a statement and a reason all together in one sentence. Then they move to the next thing. This means that XM and MY have the same measure. Okay? This means the measure of X to M equals the measure, or the length, to MY. So if two segments have the same measure, let me ask you, what do we say in geometry? We have a word. If I have two segments and they have the same measure, we say they're congruent. That's what congruent means, right? What does it mean to be congruent? Two segments have the same measure. By the definition of congruence. By what it means to be congruent. If two segments have the same measure, then they are congruent to each other. Well, therefore, segment XM must be congruent to segment MY. So this one really had two main steps to it. And I'm going to write out those two main steps in an outline proof. This is called an outline. Sometimes it's called a formal proof. And this is going to be the most common way that we do proofs. The very first thing we do is make all our statements. And the very first statement is our given statement. M is the midpoint of X, Y. How did we know M was the midpoint of X, Y?
Said so.
They told it. They said so.
Yeah.
The reason we write is given. That's what was given to us. They said, hey, we're starting with this. Then, number 2, let's see what they said up here. They said from the definition of midpoints of segments, we know that the length x to m equals the length from m to y. Their next statement was length xm equals, you can look at the picture, length my. How did they do that? What is the reason they said that this must be true?
Because M is the midpoint of X, Y.
The definition of a midpoint. Definition of a midpoint. Definition of midpoint. Then they said, number 3, xm, a segment, is congruent to my, the segment. Now you can look back in the paragraph proof. Tell me what the reason. How do I know that's true?
Because the definition.
If two segments have the same measure, by definition, they are congruent. So this is called the definition of congruent segments. Now, this is what we teach you with proofs in geometry. Deductive reasoning. Logic is what we're going through as doing these things. If this is true, and they're saying this is given to us, then I know if I have a midpoint that these two lengths must be equal. And if those two lengths are equal, I know that those segments must be congruent. And here are the reasons why, which leads us to a theorem. And this theorem says, if M is the midpoint of segment AB, then I know segment AM is congruent to segment MB. All the postulates and all the theorems you need to know. So we already talked about 7 postulates up there. You need to know them all. And here we have our first theorem. You need to know that theorem. It has a name. It's called the midpoint theorem. If I ever need to use this in a proof in the future, if they ever tell me that I have a midpoint of a segment, I can conclude that I have 2 congruent segments from it. And my reason is the midpoint theorem. That allows me to conclude that. So in geometry, when we do proofs, your tools are the postulates and theorems and definitions. You have to memorize them. You have to know them. I'm going to start you with a worksheet. You can turn to a partner.
Jump to another.
Hey, you know what?
Jump to
Or are you from going to group 1, 2, or to group 3?
When I got you, whenever I got you, what did you say?
I'm writing the bookwork on the wall.